This video is about the pH scale. By the end of this video, you should understand the pH scale in terms of the autoionization constant for water. You should be able to identify acids and bases based on pH. And you should be able to calculate pH for a strong acid or a strong base. In order to understand where the pH scale comes from, let's consider how water can behave as both an acid or a base. Recall that water is an amphoteric substance, meaning a substance that can behave as an acid or a base. Water undergoes something called autoionization. Autoionization is the transfer of a proton from one water molecule to another. It's laid out in this diagram here. Notice our first water molecule donates an H+ to another water molecule, giving us a hydroxide ion and a hydronium ion. This happens to a very, very small extent in any sample of water. Since this is an equilibrium system, we can describe it using a K value. Kw, which is the ion product constant, describes the dissociation equilibrium for water. It's important to note that this is temperature dependent. So from here on out, we'll be talking about Kw at 25 degrees Celsius, which is generally around room temperature. Though when we're working at temperatures other than 25, the Kw value will vary. Looking again at our autoionization of water reaction, we can write a K expression for this reaction. Again, we don't include H2O liquid because liquids are not included in our K expressions. And we can choose to write it with hydronium or with H+, same thing either way. At 25 degrees Celsius, pure water will always have an H+ concentration of 1.0 times 10 to the negative 7th molar. Likewise, it will have an OH- concentration of 1.0 times 10 to the negative 7th molar. Therefore, the Kw for pure water at 25 degrees Celsius is 1.0 times 10 to the negative 14th. This is a fixed value at that temperature and will not change so long as your water remains pure. So how does this get us to the pH scale? Well, it turns out that in any aqueous solution at 25 degrees Celsius, if you multiply the H+ concentration times the OH- concentration, you will always get a value of 1.0 times 10 to the negative 14th. In neutral solutions, H+ concentration and OH- concentration are equal, both at 1.0 times 10 to the negative 7th. However, in acidic solutions, our H+ concentration is higher than our OH- concentration. In basic solutions, our H+ concentration is lower than our OH- concentrations. However, in every case, if you multiply these two values together, you'll get 1.0 times 10 to the negative 14th molar. Again, this is only true at 25 degrees Celsius. This forms the basis for the pH scale. The pH of a solution is found by taking the negative log of the H+ concentration. Consider the fact that we could just determine acidity or basicity by talking about the H+ concentration. But since these tend to be very, very small numbers that need to be written in scientific notation, it's much easier to take the negative log of these numbers. For example, take a neutral solution at 25 degrees Celsius with an H+ concentration of 1.0 times 10 to the negative 7th. Taking the negative log of this H+ concentration, and we get a pH of 7. Interestingly, at temperatures other than 25 degrees Celsius, the neutral pH will not be 7. At temperatures above 25 degrees, the neutral pH will be less than 7. At temperatures below 25 degrees Celsius, the neutral pH will actually be greater than 7. It's important to note that this is a logarithmic scale. Therefore, each pH change of 1 is a tenfold change in H+ concentration. You're likely familiar with the pH scale. Here we see that a pH of 7 is neutral, and acids have pHs less than 7, bases have pHs greater than 7. Just as pH is the negative log of the H+ concentration, we can also define the term pOH, which is the negative log of the OH- concentration. Obviously, as one goes up, the other goes down, And we could talk about things in terms of pOH. It would do the same job. It's just by convention we choose to talk about pH. Due to the relationship between H plus concentration and OH minus concentration, when we add pH and pOH for a solution, we will always get a value of 14. Therefore, if the pH of a solution is found to be 2, its pOH must be 12. The graphic shown here shows you how to get back and forth between each of the values we've discussed. When given the H plus concentration, you can determine the pH by taking the negative log of the H plus concentration. Conversely, if you're given the pH, you can determine the H plus concentration by taking 10 to the negative pH. This is essentially the opposite of taking the negative log of something. This same relationship holds true for pOH. pOH can be found by taking the negative log of the OH minus concentration, and OH minus concentration can be found by taking 10 to the negative pOH. We can get between pH and pOH by simply subtracting from 14, since the pOH and the pH must always add up to 14 for the same solution. Calculating pH of a strong acid or a strong base is quite simple. Since strong acids dissociate completely and the equilibrium position lies so far to the right, we can assume that the H plus concentration will be equal to the initial acid concentration, since all of the initial acid has dissociated into H plus and A minus. For example, here we're asked to calculate the pH of a 0.001 molar solution of HCl. Since we know that HCl is a strong acid, it will dissociate completely. Therefore, the H plus concentration will be equal to the initial acid concentration, which was 0.001 molar. Taking the negative log of this concentration, and we get a pH of 3. Here's some examples to try on your own. Pause the video here, and when you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice in the second example, we were given a strong base. Therefore, taking the negative log of this concentration gave us the pOH. To find the pH, we needed to subtract from 14. That brings us to the end of this video. Let's review our goals. First, we looked at the pH scale and how it relates to the autoionization constant, or Kw, for water. Then we learned how to identify acids and bases based on pH, with acids having pHs lower than 7 and bases having pHs greater than 7. And finally, we looked at how to calculate the pH for a strong acid or a strong base.